Hello everyone, and welcome to Group 12's video presentation on analyzing digital outputs of an ultra-low freezer. Speaking today are the members of Group 12, Xavier Amos, David Bielowski, Oliver Bogan, and Nishant Sugg. We will be explaining our challenges, milestones, and relevant results of our project. Thank you to our sponsors Sikorsky, Tom Bryan, Joe Mariano, and Sal Mascola for providing us with an opportunity to work with them on this project. Sikorsky Aircraft is an American aircraft manufacturer based in Stratford, Connecticut. Now under the ownership of Lockheed Martin, Sikorsky provides aircrafts to all 5 branches of the U.S. Armed Forces, along with military services and commercial operators in 40 nations. When manufacturing aircrafts, a sealant is used to bind external components of an aircraft in order to provide structural support and protection from harsh environments. A new commercially available sealant is currently being used in the production process, which is lighter than previously used sealants. In aviation, weight is an essential component to the functionality of an aircraft. A pound of material saved in one place can be used effectively in another area of the aircraft. However, this new sealant must be stored at -80 degrees Fahrenheit. The freezer being currently used in the Sikorsky facility is depicted on the left-hand side. Any deviation from this temperature will result in a loss of $8,000 to $10,000 per unit of sealant. This delay will result in a revenue loss up to millions of dollars. Our goal for this project is to design a system to monitor deviation from calculated control limits, trigger an alarm when out of specification, both electronically and via a physical device, and proactively look for trends in the current data that would alert relevant parties to a possible failure event.
Like any project, there were several challenges that our team had to overcome in order to exceed the requirements set forth by our sponsor. By far the biggest challenge that we faced was the complex technical aspects of the project. Since none of us have a strong background in electrical engineering, we had to teach ourselves from ground zero. We ran into issues with the initial setup of the Raspberry Pi as it did not go as smoothly as expected. In order to overcome these challenges, our team had to do extensive research on both the hardware and software involved with a device which we had never used before. Another challenge that our team faced was communication. Although we maintained very good communication with each other and our sponsors, we had some difficulties communicating with our technical advisor. As our technical challenges began to arise, we also were not able to get into contact with our advisor, making it much more difficult to solve than it needed to be. In order to overcome this challenge, we sought out help from our sponsors who have had some prior experience with this technology and an electrical professor at UConn who was able to point us in the right direction. In the end, we were able to overcome this lack of communication. One final challenge that our team had to face was the challenge of collaboration. Due to the circumstances with COVID, not all of our members were on campus and able to meet in person. This was a fairly big challenge since we had to create a physical system that required a lot of hands-on engineering. In order to overcome this challenge, we assigned specific tasks to each team member and met often via Zoom to help each other out as much as possible. The milestones of this project have been broken down into 5 categories: research, design, approval, prototype, and finalization. In the research stage, our team had 3 big milestones. These included the project charter, the initial business plan, and the cost-benefit analysis. After the initial research had been completed, we created a high-level architecture diagram of the system to present to our sponsors. After reviewing the design of the system, the sponsors gave us the thumbs up to commence. The next step in the process was to order the parts and create our prototype. Once the parts arrived, we assembled the hardware and began working on the software. We are currently working on the finalized stage as we are beginning the testing of the system.
From our development of an extensive cost-benefit analysis and architecture diagram, we determined that the optimal solution is designing a system with a Raspberry Pi computer, a T-type thermocouple, and Splunk, a data visualization software. The single-board Raspberry Pi is fitted with this ultra-low temperature thermocouple, which reads the temperature inside the freezer through an access point. The collected data is transmitted by Ethernet to a local computer. After some coding, Splunk allows us to read the data, perform predictive analytics, and automate staff alert messages via email or SMS when there is a failure event. The simplistic design of this IoT system allows for vast adaptability and scalability. It can monitor the door of the freezer with a sensor and trigger an andon light in the case of an open door or temperature change. The Raspberry Pi can work with probes to monitor temperature, pressure, and humidity. The low cost of our design means it can be easily duplicated on multiple freezers within Sikorsky's facilities or even expanded onto other fields.
From the day we started this project, we have learned from great professionals and mentors. During the first From the day we started this project, we have learned from great professionals and mentors. During the first semester, we worked tirelessly to understand Sikorsky's pain points and deliver options. Using tools like a project charter and cost-benefit analysis, we were able to plan out an Internet of Things design and narrow our options down to a prototype that cost less than a third of their planned budget. Special thanks to Lockheed Martin professionals Tom Bryan, Joe Mariano, Alex Moses, and Sal Mascola, as well as professors Francisco Cunha and Craig Calvert. Thank you.